There used to be just a ventilation code for just smoking rooms.
Actually?
Yeah, the standard used to have smoking or non-smoking rooms and different ventilation rates for each.
I mean, for the record, good idea.
Yeah.
But also that's interesting because I'm like remembering when I was a kid when they started building those like enclosed smoking rooms
Oh yeah.
in restaurants for like that, what was it, 5 years maybe or something like that before
Yeah,
they
it was
made
like
it
a good
illegal?
like 10-year period where it was
Something
like
like that.
yeah.
Waste $30,000 on an enclosure and a big gigantic fan, and then illegal, no more smoking. But anyways, hi Shawn, how's it going?
Yeah, good.
Good.
Yeah.
Apparently we're talking about ventilation today, as is alluded to by our
Yeah.
little initial conversation there.
Yeah, actually pretty it's interesting because ventilation is really hard to see.
Yeah.
It's invisible actually.
Air is invisible.
Yeah.
Usually you just see the vents. Like I'm looking at the vent in our ceiling over here.
Yeah.
And sometimes you see some returns. I don't see one in the room here. But yeah, it's hard to see.
It's almost subconscious. Like you subconsciously know someone's well ventilated or not.
Speaking of though, because we started this talking about smoking rooms.
Yes.
If you want to test the ventilation in your house, maybe start smoking. Exactly. Pick up a smoking habit, and you'll be able to see the smoke, eddying and curling and moving all over the place. It's kind of interesting to think of. In my apartment, I put in a new ventilation system, and I've lit some incense, and then you kind of see with the ventilation system off, it's just like one line of smoke going up. Once the ventilation system goes on, it starts to kind of wobble around and circle and eddy. It's kind of fun.
Yeah, so we use smoke quite often in building science and air barrier testing specifically, but also looking for ventilation and how effective it is. You can use smoke to see the air movement.
Yeah. There's not really any way to do it otherwise.
Well, here's a hot tip.
Oh, okay.
Yeah, anecdotal reviews. So I was asked to look at a pool room that was having some moisture issues.
Moisture issues being condensation in places?
Yeah, so the condensation is happening down the hallway, sort of like the pool, like when you go into a hotel and you can smell chlorine in the lobby, you've got a ventilation problem.
Definitely.
The balancing's not there.
Unless it's just advertising the pool. Maybe it's on purpose.
Yeah.
I doubt that.
I've been to hotels for like, is this the right pool room floor?
Yeah.
No.
Yeah, that's the floor below. It was just like infiltrating upwards.
But what you can do if you don't have smoke and you're not going to start smoking, is toilet paper. You take a piece of toilet paper and hold that up to your door, and which way the door blows, will tell you which way the pressure is. I refer to that as air leakage tracer paper in my report.
Tracer paper. That's a nice. Actually, that like the initials line up well. Tracer paper, toilet paper.
Yeah.
So you don't have to think about that part of it. It's nice. Tracer paper.
But to fix their condensation problems down the hallway, like in the lobby. We basically changed the mechanical balance so that there was more negative pressure in the pool space than positive. So we got to it was a balanced system, and we can talk about the difference between those.
We're going to get into that. Probably should define that, but
yeah, essentially that's a common problem with pool enclosures. The balance is wrong, and they're pressurized. They should be negatively pressurized.
Sure. So yeah, like I guess let's take a couple steps back and talk about the different types of ventilation, how it works, how it doesn't work. But in general, there's three, I guess, types of ventilation, or three different scenarios of ventilation. You have negative pressure, you have positive pressure, and you have balanced pressure. And really what that is if it's positive pressure, you're pumping extra air into the room and hoping that it goes out through gaps.
Yeah, you're blowing up a balloon, basically.
Exactly. Negative pressure is you're depressurizing, you're sucking air out of the room and hoping that it comes in through other gaps. And then balanced is you're taking it out, putting air in. Ideally, it's balanced. Usually, is it actually like 100% balanced, or is it usually slightly tipped in one direction or the other? Probably depends on the rooms and where the vents are and things.
Yeah, so when you start getting into pressure differences across your room or your enclosure, you're into really small differences. So even if you had I'm thinking back to an RDH study from Canada looking at apartment buildings.
Sure.
And when those ran like their kitchen range hood and all the bathroom fans, it was like a 15 Pascal difference.
And when we're saying a kitchen and a couple bathroom fans, that's like a lot of liters per minute, or
it's like all the it's negatively pressurized. All the fans you have in your apartment building, was creating about 15 Pascals difference across the building enclosure, and like stack effect from top to the bottom of your floor is like
way more than that.
It's like, depending on the temperature outside and inside, that kind of stuff.
Height of the building,
it's in that same order of magnitude. So like, you run all your fans, and the top of your room might be positively pressurized, and the bottom side is negatively pressurized.
Sure.
Like,
but it's such a minute difference that you don't really necessarily notice.
Yeah. So just like, it's almost like a theoretical balance between positive and negative. And like you draw it on the page, the HVAC designer is drawn on the page as balanced.
Sure.
It's not actually going to be necessarily that.
Well, yeah, because you have, I guess, for lack of a better word, wind blowing against surfaces in the house. Just because if you have a vent here in one room, you have a vent over there in another room, the air has to make a pathway.
Yeah.
But when you said 15 pascals of pressure, I know what that means, but 15 pascals is pretty low. When we do a blower door test for like a passive house, usually we're pressurizing and depressurizing up to, what is it, 50 pascals, if I'm remembering correctly?
50 or 75, depending on your standard.
5.0 or 7.5 as opposed to 1.5, which is the pressure difference from a little bit of sucking air out of the house, essentially.
Yeah. It will, so the air's moving, like the fan is blowing. It's, small fans, bathroom fans I'm talking about. Yeah. We can talk about larger HVAC, like commercial spaces is different, different story. But when you're talking about like residential sized mechanical systems, they're moving air.
Yeah. You can feel the wind, especially on the outside if it's an exhaust fan.
But it's not necessarily going to create this large pressure difference, which is going to, suck moisture through your walls either one way or the other. It's like a theoretical pressure difference.
Sure.
Which you probably can't measure in most cases. Unless you have a very airtight building, you're probably not going to measure it. So in most cases, if you're retrofitting a building particularly, a negatively pressurized system just extracts is completely fine without having make up fresh air or forcing air in. Because you're not actually creating a pressure difference.
I see where you're going with this. Yeah, and like I've had these conversations in project meetings before where I say, let's put some continuous negative extract in a bathroom, and that'll just constantly cycle a little bit of air through and pick up moisture and dry things out. And usually the first a question from a mechanical engineer is we have to put makeup air. We have to have a vent somewhere. We have to have undercuts under the doors. We have to like specifically design
technically correct
trickle vents or something like that. Technically correct. But in practicality, in reality, you don't really need to have a specific vent for that makeup air because it'll just come in through gaps around the windows, gaps around the doors.
Well, the pressure difference you're creating with a small bathroom fan is like 1/100th the force of the wind across your windows.
Sure, exactly. Exactly.
I guess I'm in the same world of
you're not going to break the windows, you're not going to break your air barrier, you're not going to break sealants.
No, it's like I always imagine like somehow people think like the walls are going to cave in.
Sure.
If you turn on your bathroom fan.
Yeah.
It's not even close to that amount of force.
And you couldn't get it to that because it's not airtight enough to get it to that pressure. Because as you increase that pressure, you start losing anyways.
Yeah, I'm sure there's a technical term for this, but like zone of influence or area of influence is sort of the way I think about it.
Sure.
This is a really common one for bedrooms specifically that have en-suites.
Okay.
Bedrooms with ensuite bathrooms, leaving that fan on there, it ventilates the bathroom and then also pulls air out of the bedroom, which is where the moisture's happening during the night, just for sleeping reasons and for other activities.
Who knows? More or less water sometimes.
Yeah.
But even just sleeping, you're breathing out so much moisture, and that's why you wake up in the mornings with a single glazed window or an aluminum frame, condensation on it, because there's just more moisture in the air.
Yeah.
But if you have that constant extract, even if it's coming from the bathroom, it'll slowly pull that moisture from the bedroom and exhaust it.
Yeah, so it's an area of influence. Like the ensuite will extend to the bedroom, and it won't probably necessarily go down the hallway to the next room. I don't know. There's probably a calculation there someone's done, or if you know of some research around that, like how much airflow can service a small area.
I'm sure there's some either CFD modeling or they've gone in with like a tracer gas or something like that and seen where all the wind goes. There's got to be some study somewhere.
The standards like ASHRAE 62.1, 62.2, they'll give you some rule of thumb on how far ventilation per square meter, square footage that can be ventilated by a certain fan.
Sure. But that kind of is just more of a based on a certain set of assumptions, a certain amount of air.
Oh, it's like a rule of thumb. I'd love to see some actual CFD modeling sort of thing. But generally, if you're using an ensuite bathroom as your ventilation for a bedroom and a negative pressurized situation, perfectly fine.
Absolutely.
Perfectly great solution.
Yeah. cheap, cost effective, doesn't cost.
You already got a fan there.
Yeah.
So you're maybe spending extra $100 on a better fan.
Better fan. I think the other complication is like you have to wire the switches a little bit differently so that you have a constant extract and then the switch is a boost mode or something like that. But all of this is
the
like
fans have that built in.
Sure, yeah. And but yeah, it's like a couple $100 extra really, and you get so much more airflow through.
And the other pushback I'll get to that is that they're loud. Well, the cheap ones are loud.
Absolutely.
The quiet ones, you don't know they're on.
Yeah, especially like if you have like an inline one that's inside the ceiling cavity as opposed to at the mouth of the opening.
Yeah, very, there's ratings for sound. I don't know what the dB equivalent is, but what I'm used to specifying is what's called a SON. And a SON, S-O-N-E-S.
S-O-N-E, okay.
And one SON is like audible, like you can actually hear it.
Okay.
And these fans are at 0.3 SONs.
Okay.
So these are like library quiet fans.
Yeah.
Which, like I said, if you didn't know they were on, you wouldn't know they're on.
Yeah. As anecdotal evidence, I got a new ventilation system in my house. It's a balanced ventilation with heat recovery. It is a ducted system. It is in like one of the attic spaces in my apartment. And it goes into my bedroom, goes into the other rooms as well. In the bedroom at night, when it's fully quiet, I can hear the ventilation system, but it's like the smallest. I don't know if that'll come up on.
See if audio picked that up.
I hope so. Did you hear that from my side?
Yeah, I can hear you.
Yeah. So it's like this small amount of noise, but it's just background white noise. You don't really notice it, and you fall asleep perfectly.
My 2-year-old son sleeps with white noise constantly all night.
Sure. Yeah. There's apps you can get. There's like little devices you can get, and people travel around with white noise.
One of the common white noise
is fan.
Box fan.
Yeah, absolutely.
Super common.
Mm-hmm.
Probably in the South. That's probably from the South.
What do you mean?
You wouldn't use big box fans a lot in like the north part of North America.
True.
You're trying to move air through the house in southern part of the U.S.
Yeah. I had a big box fan in my old apartment because I just needed to move air through, especially in the summer to cool things off.
Yeah, sometimes that's the other thing we probably can start talking about is how ventilation can help with overheating.
Sure, absolutely. Let's finish off. Okay, so we talked about 3 different types: positive, negative, balanced.
Yeah.
We can dig in a little bit more. So once again, positive is like an extract fan, like we were talking, constant extract in a boost mode. Positive pressure, I don't like it. I don't recommend it. Personally, there are scenarios where positive pressure is a good thing and you might need it. But for houses, having negative is much better. Having a balanced is even better than that. And I know you mentioned that
so the only spot of positive pressure would be useful for is if you're doing something inside that space.
Sure.
That can't have contaminants from the outside.
Absolutely.
Spray paint booth, something like that.
Absolutely. Clean rooms in hospitals. I've seen those. But what they usually have is a pressurized room and then a depressurized room outside of it exhausting, I think. Could be. That you don't get contaminants from the outside going in, but also you don't have contaminants from the inside going out, hypothetically.
Yeah, but if you're designing one of those, you've got a specialist that's already involved designing that HVAC. You're not doing it by accident.
And you're also making that room very, very, very airtight.
Yeah.
As well. Yes. Whereas with a common house, there's, the power points and switches and things like that, lights that are embedded in the ceilings, lots of things. So with the positive pressure, one example is all the, those box fans, well, not box fans, a fan in a box with some ducts that have 3-letter acronyms. There's multiple suppliers in New Zealand. And they put a box fan in the fan in a box in the attic, and it sucks out the attic air and pumps it into the house, and says that they have heat recovery because the attic gets hot sometimes, and sometimes it pumps that hot air into the house. So those are the ones that are common in New Zealand, and they technically would work in a villa, an older building, because any ventilation is better than no ventilation. And if the building's super air leaky, then So
there's a good question. Is any ventilation better than no ventilation?
Okay. I just said that very definitively, and now you're making me rethink it. But I think so. I think a little bit more ventilation is better than not.
Let me ask a different question. Okay. Could you take an old villa that's working?
Yes.
And could you fuck it up by positively pressurizing it?
Positively pressurizing it. Old villa, this is like a stock standard. It hasn't been insulated over time. It hasn't been made more.
Is there a scenario where
I see. I asked the right question then. So yes, if you have a older villa where you've increased the insulation, increased the air tightness, kind of plugged things up, and it's not working as originally designed, and originally designed means no insulation in the walls, a little bit of, air leakage through the weatherboards, fireplace on all winter. If you didn't use the fireplace all winter and then positively pressurized it in the winter and you had extra insulation in the walls, then yes, you could definitely cause problems.
Yeah, think about the ventilation from a fireplace.
Yeah.
It's like it's full noise.
A staggering amount of ventilation.
It's all the ventilation you can handle.
Yeah.
There's actually a good Mythbusters on fireplaces.
Is there?
Yeah.
Okay. Describe. I don't remember seeing this one.
So if you have an old villa laid out with a fireplace, you light a fire in that room and it goes up the chimney.
Yeah.
It's drawing then cold air from all the other rooms in the house.
Because it's feeding the fire with oxygen.
Feeding the fire.
And then
it actually makes all the other rooms in the house colder.
Sure. Yeah. And I mean, that...
They measured it.
Anecdotally, you probably have noticed this in your own house if you've lived in a villa, that you put on the fire and you're nice and warm in front of the fire, but anywhere that you don't feel the actual radiant heat of the fire, it is technically colder. Unless you have a closed fireplace that is, it's got its own air supply, its own fan to blow convection air around kind of thing. There's different fires, obviously, but...
Yeah, we're talking about open flue. Yeah. Like open face fireplaces.
Yeah.
There are some really high-tech fireplaces. Like, really efficient ones.
Yeah. With and you don't even have to have a chimney anywhere. You have like mechanical flues with fans inside them.
Oh, we're going to have to do a heating episode.
Sorry?
We're going to have to do a heating episode.
Absolutely. But yeah, okay. So positive pressure, box in the attic with a fan in it. I think they're not good because they're expensive and they kind of just pull attic air and blow it into the house. And sometimes it works, sometimes it doesn't. Sometimes you're more comfortable, sometimes you're not. There's a screen on the wall that has like temperatures and...
Doesn't sound predictable.
Yeah, that's the main thing.
One of the key principles of ventilation is predictability.
Yes. And with those attic systems, they have the screen on the wall and like it measures the difference in temperature between the inside and outside and like changes the fan speed and stuff like that. I don't really understand how they are meant to work logistically, but my balanced ventilation system just runs 24/7 and it always is good, comfortable air because it, gets heat recovery as it pulls air in and exhausts it.
Yeah. So you just retrofitted your apartment with balanced heat recovery,
ducted system.
Filters?
Yes.
Tell us about the filter part, because I think the filter part is really underappreciated.
Okay, sure, yeah. It has a filter on the way in. I don't think it came stock with a HEPA filter, but it is a fine particulate filter at least.
Yeah.
And so I think I have to replace them every 6 months to a year, depending on how often I'm using it and depending on how dirty the air is. But the nice thing about it is I can close up my windows. I can be comfortable year round. I can do that in the summer and in the winter. Always have that fresh air. And the fresh air is also filtered and cleaned from the outside. So I'm an allergic person. I have a lot of hay fever allergies.
Oh, yes.
The pollen gets filtered out. If there's smoke in the air, that mostly gets filtered out depending on your filter. The smells, like, I don't know how much they get filtered out, but I don't really smell anything inside my house. It smells clean. And also, if there's anything inside my house, if I've been cooking and there's smoke involved, if, I don't know, like I'm drying off my laundry inside in the winter, because you have to do that in the winter, it's constantly cycling that air and exhausting moisture and exhausting any smells and smokes and things like that. So
I saw
pretty well.
A presentation years ago, maybe a decade ago.
Yeah.
And it was someone from the health side of ventilation that was talking about why are we ventilating. People have been talking about CO2 concentration as being like the reason that you want to ventilate. And that's partly true.
More of a marker.
It's a tracer, like you'll start to see effects like at 1,000 parts per million, but really like 10,000 before you start to get really noticeable.
Sluggish, yeah.
And so I put up a graph of like the things in ventilation that would kill you, essentially. And it was like VOCs, like benzenes and smoke or CO2 or all these things.
Sure.
By far the biggest killer or health risk of not ventilating is particulate matter.
Oh.
Particulate matter, by far the leading cause of any lung cancers.
When we say particulate, we mean dust or like any particulate?
I think all particulates sort of act pretty similar at that 2.5 micron level.
Sure. Okay.
It's like you're in pollens, you're in dust, you're in...
Goes all the way into the...
Yeah, it penetrates down deep enough and causes the problems. And I think, I'm sure there's some that are more hazardous than others, but as a broad category of things,
sure,
that's the one that's like the leading problem. And then talking to people like Asthma New Zealand about this, they're like, yes, we know this. Asthma is like triggered by particulate matters. And a lot of the someone will have better research than I have here, but anecdotally, if we control particulate matter, we have a better outcome on health than trying to ventilate for moisture.
Okay. Interesting. And for CO2 as well.
CO2 being a tracer to say you have enough ventilation for the number of people in the space. But one of the reasons that New Zealand has particularly high asthma rates is we have particularly high pollen counts for some of the native bush here.
Yep.
So
I noticed that with my nose.
I've noticed it too. I not have allergies in Canada whatsoever.
Yeah.
Here on occasions I have them.
Yeah.
I think I have some mold allergies as well at certain times.
Yep. Same.
From housing.
I've noticed that the mold isn't even just from the housing, it's just from outside, because if you walk through the forest, like we're in Auckland, we go to the Waitakares, and there's mold growing on the trees. You get a thunderstorm, you get a windy day, it blows those spores over to the city. So yeah, windy, rainy, thunderstormy days are worse for me.
Yeah. So then you take that perspective. We're trying to control particulate matter in spaces, hospitals, schools, houses, whatever it is. How is Windows going to do that? How is Windows going to...
When you say Windows, you mean like opening your windows?
Natural ventilation.
Yeah.
Natural ventilation, unfiltered natural ventilation. Well, the thing that's trying to kill you is outside.
Sure.
So if you're going to invite more of it in, you need to filter out the bad stuff before it comes in. So if you're going to... You can use natural forces, natural ventilation, naturally forced ventilation, maybe is a better way to say it.
Okay.
Is you can bring fresh air through filters naturally.
It takes a lot more design, but
way more design.
But
way
you
more
can
complicated.
Do it. Yes.
Just opening your window is basically not going to really have the health impacts you're hoping for.
Well, yeah. And I mean, like you get your indoor-outdoor flow, you get the feeling of outside, you hear the birds chirping and stuff like that. But
which is all relevant.
It's all great. It's all good stuff. And on nice days when it's nice outside, then even me, like I open up all my windows and doors. But on days when it's kind of bad outside and like there are things out there that want to make me cough, it's nice to be able to close windows and have filtered air. It's
there's a space for natural ventilation. It's just not as simple as opening a window.
Correct. Yeah. And there's a lot of old buildings in the world that have been designed for natural ventilation. I know there's like, I feel like there's one that I was reading about in some deserty type city somewhere in some country that they have like underground, like a well and a tunnel that picks up air. It brings it down into the ground to cool it down, and then it gets stack affected up through the building, and it cools off the building to make essentially
some stuff like that. I've seen stuff like that in Alaska.
Oh,
bring fresh air in through tunnels to preheat it.
To get it, because you have like the ground temperature is warmer than the air
you're bringing in like air at like minus 40.
Sure.
So you're bringing fresh air. If you run it through underground ducts first, you can get it down to like up to like minus 20.
Which is easier to heat. It's cheaper to heat.
It's like almost free.
Speaking of that, there was a building that I went to inspect in Toronto that it was like a high-rise building, old one from like the 60s, one with, brick and exposed slab edges, one of those typical, high-rise, lots of apartments. They put these boxes on the outside of the building. So one of the elevations didn't have windows on it. And so they put this big black metal box on the outside of the building and then sent the ventilation through that in the hopes that it would warm or preheat the air in the winter. It apparently did not work as well as they thought it would. I feel like there was maybe some aspirational assumptions made in the design and it just didn't quite work the same way that they wanted it to. Or maybe it worked, but cost benefit didn't really work out. Can't remember what it was.
This reminds me of trom walls and passive solar design.
Trom walls?
Yeah.
What is this?
The trom wall is like you build a glass enclosure.
Okay.
And then between the glass enclosure and your living space, you put a gigantic concrete mass wall.
Sure.
And then you have an opening top and bottom. The idea is you use the sun to heat up this concrete wall, and then stack effects is going to bring ventilation through. And it doesn't work.
In certain scenarios, on the right days, it would maybe kind of work somewhat. And for a certain amount of hours, maybe.
Yeah, heinously maintenance heavy to make that work.
Yeah.
It's like it's a science project, it works, but as a general population, no.
Yeah, and I feel like that's also kind of the conversations that I have when I'm talking to people about ventilation or just in general design. There are certain houses that people have built for themselves or have had built that I find are they work, they're effective, they're probably warm, they're probably comfortable, they're probably very energy efficient, but it takes a lot of user input to make that happen. I've seen houses with lots of shutters on the outside, windows to open and close, and all of it's manual, and all of it is, solar passive as opposed to passive house. And
it's like the difference between driving a manual transmission car and automatic car.
Like, yes,
like
but I'd say like an old tractor from the 1920s with like 15 levers to pull and this thing over here and all kinds of complicated things that you're trying to hand, feet, grabbing something with your teeth. Whereas if you design a house that just kind of does its own thing, you have some things maybe that open and close.
It's like driving a Tesla or an automated car, like self-driving.
It figures itself out. It knows what to do.
And everyone can drive that car.
Yeah.
Right? Not everyone can drive a manual stick Porsche 911.
Not everyone wants to. Like some people love that. They think it's a great thing. And for you, great. If that's your house.
But as a general population design principle, not a good idea.
Yeah, like least resistance is what you want. You want a person to just walk into their house, feel comfortable, and not have to do a bunch of extra work to make it comfortable. And I think ventilation helps that. I think balanced ventilation with a heat recovery exchanger inside of it also helps that, because it can just run all the time. It warms up the air as it's coming in, it dries things out, and keeps everything fresh.
Now, on the topic of natural ventilation, how often do you think the weather outside in Auckland meets the humidity and temperature criteria for comfort? As a percentage of the year.
So I don't know the exact number, but I know what you're referring to because I've done this rabbit hole dig. So like, just to define what you're trying to say, indoor temperature that is comfortable and like within a good range is like 40 to 60 relative humidity, 40-60%, and between like 18 and 25, if we want to use the definitions from Passive House, 20 to 25, let's say, is more comfortable.
So in that range, my frame of reference would be ASHRAE 55, which is a bit more nuanced than that range, but that's fine for, So ASHRAE 55 is like a population samples of like people in offices, like they walk around or something, like, do you feel comfortable right now?
Yeah.
No? Okay. No.
Okay, that temperature and
this look at kind of clothes you're wearing and do some surveys like that to figure out like if you design it within this box, it'll be comfortable.
Yeah. And these are like rules of thumb, but based on very much real world evidence.
Oh, like decades of research and like, we did that and that actually didn't work.
So within those bounds of comfort of certain temperature and certain relative humidity, how often does the outside air match that? 10%?
Oh, it's much less than that.
No, less than 10?
I think it's 2%.
Oh, God. So 2% of the time, you actually want the outside air to be inside to be a comfortable temperature and relative humidity.
Yeah. Now, there's tons of caveats on that.
You're talking about Auckland?
Yes.
Cool.
Auckland, yeah. So you can Climate Consultant 6, a free software program.
Go download it.
Really fun to play with.
Pretty easy.
You can download basically weather files from anywhere on the planet, plug them into like a adaptive model, and it'll tell you some strategies how to ventilate your building, heat your building, cool it, shade it, whatever it needs to do.
It basically puts a big psychrometric chart with a bunch of data points on it and boxes for if you do natural ventilation and no heating and air conditioning, this is the comfortable range. And then as you do more things, it expands that comfortable range.
Yeah, so it gives you weather data and a bunch of different graphs and displays, and lets you like really understand the local climate and then what to do about that particular building.
Sure. And so like 1 or 2% of the time is the actual comfortable temperature outside to bring inside.
Yeah, so if you're just talking about the weather, it's that. But then there's a bunch of like other things that go into comfort, like internal heat gains, with just like your body temperature or your pets or TVs or whatever it is.
Machinery inside, if it's a big
that alone is like I think 20 or 30% of the comfort.
I see.
So that's where natural ventilation sort of makes sense. It's like 20-30% of the year it's comfortable to just open up the outside. And
because you have residual heat inside that will heat up and dry out that air coming in naturally, maybe.
Kind of. More of the part of it's reducing humidity, but temperature.
Sure.
So that's like a big contributor to it.
Yeah.
And the other part is shading and sun exposure.
Sure.
It's not quite in that model because I'm just talking about the actual ambient temperature in the shade.
Sure.
So if you're bringing in sun to that, you've got another sort of other set of variables to contend with.
Air movement? Does that factor in as well?
Probably. Well, it does. Because here's the other part is like, so if you have overheating concerns in your house, or you have an overheating problem in general in any design or house. And we can do this. We do this in the models all the time. You set up your model with whatever clear glass, stock ventilation rate, and we get overheating 17% of the year or something crazy.
Sure.
The first variable I always look at is, can we just run a summer extra ventilation?
Sure.
Can we take that air change rate from like a half an air change per hour to like a 2.5 or a 3, which is absurd any other time of the year. But if you're using it just to control overheating, it usually works. And so what I explain to people is like, is the climate in Auckland generally comfortable in summer most of the time?
And the answer is yes.
Or British Columbia, or tons of places on the planet, right? So when overheating is happening, it's usually, in the places we work at least, it's quite comfortable in the summer. Like, this wouldn't work in Phoenix or Austin or Miami or something like that. But
even Winnipeg or Toronto during the summer, it goes up to like 35, 40, and even overnight it stays pretty warm.
Yeah.
But here in Auckland, especially, like usually overnight in the summer, it's going down below 25. In the day, it'll only go up to 28, really. Like it doesn't go even to 30 usually.
Yeah. So what I explain to people is, if you live in a climate that is generally comfortable outside through the summer period, and your model says that in the house you're going to be too hot, that means you have too much solar gain coming into the house. You've created a greenhouse.
Something's up. Yep.
So then I explain it. If you mix the air so fast that the air inside couldn't heat up, and is just like the outside, would that be an acceptable range of answers for you? And for a lot of people, like
most of the time in Auckland, at least, and most of New Zealand,
it's like a 2% exceedance on temperature. Humidity is a different question, but temperature is like, you can get there pretty quick.
Yeah. The other thing that I've suggested on certain projects, and I don't think I've gotten them, is specifying ceiling fans. Because even if the temperature, the comfortable range is defined as like 18 to 25, 20 to 25 degrees Celsius, something like that.
That's got a big asterisk beside it.
Of course. Yes. But like general, expectations. With that, even if it goes up to 28, like that feels warm if you have still moist, humid air. But if you have a fan on and you're maybe sweating a little bit, that'll cool you off because just that air movement feels much colder.
The standards actually have criteria for air speed across skin from which direction it's coming. You can. Ceiling fans are a really cheap way to, like, you're talking about something that's got like a 2% of the year you're going to use. It's like a ceiling fan is like probably the same, whatever light you're going to put up there. It's the same price probably to put a ceiling fan.
I was looking at them in Bunnings the other day. They were like $400, $300, $500, depending on how fancy they are. If they had a light and if they had different settings or whatever. But like fairly cost effective. To really improve your comfort.
Can also help you with the heating as well.
Sure, yeah, because it mixes up the air.
Yes, if anyone's ever wondered why your ceiling fan has 2 directions in it.
I learned this very early on because I'm like, why was that? And I kind of thought about it, like even as a kid. But a lot of people don't necessarily notice or realize.
So in one direction, it's going to force air downwards, and that would be your cooling direction. Like, I'm lying under the fan, and I want,
because you want to feel the air. You want it blowing against you. Yeah.
But in the wintertime, you're going to use it actually to circulate air. So you're going to reverse the fan blades, is going to force air up to the ceiling, out to the walls, and help you mix that heating more continuously. And so you look at thermal comfort, and the standards vary in depth on like what people feel comfort. And one of the things is difference in temperature. So if your ceiling's very warm and your floor is very cold, that will be more uncomfortable than if those were the same temperature. And we talk about we always talk about air temperature at 20 degrees. It's actually the mean radiant temperature that you're measuring, which is air temperature and then the effects of all the things.
Surfaces around
you. It's much more complex than just air temperature.
Yeah, definitely. And like that stratification, it gets even more, I guess, intense. Like I have in my apartment, we're going to talk about my apartment apparently because that's what's in my mind. I have very tall ceilings and they're kind of like sloped cathedral ceilings, skillion roofs. And with that, all of the heat just kind of sits up at the top corner. And so during the winter, what I would do is I would just have a big fan and blow it up against the ceiling so that it would shoot that air around and just kind of mix everything so that I get, a lot more efficiency out of my heating system, and all the surfaces are warm instead of having hot up here, cold down there, and just uncomfortable. Interesting.
Yeah, so ventilation is not just fresh air; it's about moving air around. And like I said, it's invisible, so it can. It's like you probably don't. Well, you probably subconsciously notice it.
Yeah. If you sit there and really start to think and feel sensations, you probably start to notice a little bit more. Sometimes I'll be in a meeting and I'll be in like a conference room and I'll just like notice either it's very noisy because they put the air handling unit inside that room instead of somewhere else. Or I'll feel the wind like blowing on my skin, or it'll be like one duct over here blowing a whole bunch of hot air, and kind of you can feel when it's a very good system and you can feel when it's a very bad system. Yes. If you really feel all the air and you feel hot over here, cold over there, it's just
you notice bad systems, you don't notice good systems.
Yes, exactly.
Yes. We have to talk about trickle vents before we end this.
Okay, we'll talk about trickle vents. Can I say one thing though? Of course. Have you watched Community?
Yes, I know of it, yes.
Have you watched, there's one episode where one of the characters, Troy, goes and starts HVAC training in community college, and they take them into the room temperature room. And so they walk him into this room, and he's like, what is this? And he's like, do you notice? And it's like, I can't tell where my skin ends and the air begins. And so it's just like, this is the room temperature, the same way that, you know, for 1 kilogram, it's that like sphere of platinum or something like that. That's what the 1 kilogram is measured against and stuff like that. There's actually like a
reference.
Yeah. So room temperature is where, you know, you don't feel warm, you don't feel cold, you don't feel anything. And that's very good ventilation.
Yes.
Whereas if you feel a whole bunch of stuff, then there's some failures there. Interesting. So trickle vents, we mentioned them at some points. We mentioned them in reference to like negative pressure ventilation. What did you want to mention about them out of curiosity?
Yeah, so trickle vents were the response to this fear of negative pressurization of buildings.
Oh, I thought they were just a way to get the tick box of 5% of the wall area being operable as a ventilation.
That's New Zealand thing. It's been around for decades, and Seattle's in their building code.
Okay.
Seattle building code, you have to had to have trickle vents as makeup air for your negative.
Super weird to me because in Toronto, I've never seen a trickle vent.
Oh yeah.
Yeah.
No, someone in Seattle decided this would be a great idea for everyone to have trickle vents.
And I mean, like, technically, I see the logic. I see the point behind it. You're negatively pressurizing. You want to have a space for the air to come in. But
okay, here's the one caveat about negative pressurization systems.
Yeah.
Is if you have enough fan force to backdraft your combustion appliances, your gas boilers or gas furnaces.
Oh.
So this is the one place I will agree with people is if you have a house, very airtight house to start with.
Sure.
And let's say you have a really large commercial size range hood that can suck a ton of air out.
Sure.
You have a gas boiler or gas furnace, which is burning natural gas, and it goes up the flue.
Sure.
If your fans are so powerful, they can actually reverse the flow. You can actually backdraft exhaust gases into your house.
Sure.
Okay, I agree with you. You should have makeup ventilation to prevent that.
But you can put just one vent in that specific location. Mm-hmm. I've seen it even for like fireplaces where you have your little fireplace boiler or whatever, and then a vent right next to it.
It's like a hypothetical situation that no one's ever. I can't recall of any anecdotes of people being harmed by backdrafting of flues. It's plausible, but
yeah, my ventilation system has a setting such that if I had a fireplace or if I had like a huge range hood, it does the makeup air for it, like automatically. It senses that pressure difference.
Yeah.
So like technically it's but like you said, it has to be a very, very, very airtight building, and you have to have some like industrial strength fans pulling all kinds of air.
Yeah, so if a perfect combination of things came together, you could potentially backdraft a flue, and in concentrations high enough to kill someone, probably not. But anyways, trickle vents were the answer to that in some respects.
Okay.
The research on use of trickle vents is quite interesting. And there's particularly one study from the UK looking at trickle vents. Sure. And
UK loves trickle vents, by the way.
Yeah. So trickle vent is either actively being used by the participant, like they know how to open and close it every day.
Sure.
Or it's constantly closed or constantly open.
Sure.
They don't know about it. And, and it was like something like 75% it was just closed. They didn't even know it was there.
Sure.
5% of the time it was actually used, and like 10% it was just left open all the time.
Yeah. My friend lives in Ireland. I went to go visit her. And in her house, had each of the bedrooms had a trickle vent, and it wasn't like in the window. It was just like a vent through the wall with a grate on one side and a grate on the other side. So basically just allowing outdoor
that's
air
maybe better because at least you're like, what is that hole in the wall for?
Yeah.
Versus trickle vents are like so low profile, like they sit like within the window frame almost.
You don't necessarily notice.
Oh, well, 75% or higher of people don't even notice.
Exactly. But with those trickle vents, the ones through the walls, yes, you notice them, but like she taped hers up because it was drafty in that room.
So common.
And she had a baby in there and didn't want the draftiness to, make the baby cold. And so had to like tape that up, put a little dehumidifier and a little heater in there.
So common to see them taped up. Yeah. Or I've seen portable AC units hooked up to them.
Sure. I mean, for the record, that's not a bad idea.
Yeah.
Can't argue with that one. No. It's already pre-made hole in the wall for you. You can tape it up easily. So I think one thing I'd like to mention is there's balanced ventilation, but not all balanced ventilation is made equal, because the balanced ventilation that I have in my house is a balanced ventilation system with a heat recovery unit. Mm-hmm. All of the outdoor air comes inside. All of the inside air goes outside. They do not mix. But typically, older buildings, larger commercial buildings, they would have like a fan coil unit and a makeup air unit kind of all in one, with a mixer box, which has this like little, a little door that kind of opens and closes the damper.
Yep.
That mixes inside air with the outside air. And that is the quote unquote heat recovery that I've heard some mechanical engineers describe it as. And technically it is heat recovery, but you're mixing existing stale air with the new air.
You're not recovering the heat. You're actually just recycling the air.
Correct.
Yeah, it's not uncommon to do that in like commercial applications.
It's very, very common. I have in some projects suggested that they go with a larger commercial size or industrial sized balanced ventilation system with the heat recovery exchanger inside, as opposed to mixing the air.
Yeah.
I find that they're not common here, really, and it's kind of a very specialized thing. Were they common before you moved out of North America?
Multi-unit residential buildings, MURBs, like high apartment buildings, very uncommon to have any sort of recycling of the air.
Not even in the hallways?
Hallways there was a period of time, let's say from the 50s to the 2010,
sure,
where the idea was to positively pressurize the corridor,
sure,
with 100% fresh air most of the time,
sure,
gas-fired makeup air units, and that would cause positive pressure in the corridors, which would make its way through the units and be exhausted out the extracts.
Technically makes logical sense, but
I got a good stuff. I'll find the report somewhere, but sure. We're in a building built in the 1960s, 70s, concrete building.
Sure.
We replaced all the windows in the building because they're falling out.
Sure.
That system had a positively pressurized corridor system, and basically your extract fans were supposed to help with ventilation. But as I was going through the architectural details, there was a note on the blueprints. So it was like handwritten blueprints.
Okay.
It said ventilation by windows. And I was like, oh, what a great little snippet of like ventilation by windows.
Yep.
Perfect.
Yep.
Yeah.
And I'd be like, hey, at that time, technically correct. And I mean, didn't have to necessarily prove that. And you see what the consequences are later on, I guess.
Yeah. So like 2010s to 2020s, there was a whole range of studies on ventilation systems in apartment buildings and how they were just not really well designed. In terms of efficiency. And so it's probably changed quite a bit on that front. I'll be interested to see in Canada how that's going. And we're recording this in 2025 and just about to move to Canada and start the office there. And I'll be interested to see if we've made any progress.
I assume there's going to be some progress.
Yeah.
There has to be.
The skeptic in me says they're probably still doing things we were doing wrong 15 years ago.
Ideally, less people doing them, maybe, hopefully. Hopefully.
Maybe.
What I noticed that kind of surprised me when I was still working in Toronto is that you'd have these big makeup air units and fan coil heater units on the roof, and you'd have the ductwork that goes into the building, and it was uninsulated. And it's sitting outside the building in minus 35, minus 40 degree temperatures, and it's just uninsulated. And so a lot of times I'd go do a roof replacement project, and then as part of that, go insulate all this and wrap it all, which obviously fixes, some of the efficiency, I guess, downsides. But did you find that people were insulating ductwork? Do people kind of forget about that and kind of assume the best and just waste some energy on
Some
Heating
of
it
the
up kind of thing?
duct work, I'm talking 2010s.
Sure.
So some of the duct work was insulated duct work.
Sure.
So like metal skin and then like an insulation layer between it.
Sure.
Some of it was that.
Yeah.
A lot of makeup areas were inside the building,
Cool.
inside the thermal envelope.
Fair. That's good.
Somewhere outside for sure.
Yeah.
But you bake in that loss into your
I guess so.
calculation. Yeah.
Just oversize it a little bit.
Well, but the mechanical plants in a lot of these buildings is way oversized.
Sure.
Because they're designed for, a lot of times they're designed for peak energy demand, peak heating, peak cooling. And you're not running that 99% of the time, 95% of the time.
Yeah.
So you've got baked in extra efficiencies. Now, I did work on one building that was so oversized that the cooling plant was turning off and on like
too quickly,
dozens of times per hour.
I see.
Like it would run it was a chilled water system.
I see.
So it would chill water at the top, run down pipes, and then in the units there was a heat exchanger.
Yeah.
And it was running like stop cycles was something like 12,000 per year or something.
Oh God.
It was like
not good for this.
So it's like cycling on for 3 minutes to reach temperature or reach temperature down, and then
I see.
It was so oversized they had to put in a second chiller beside it that would run like 75% of the year. They use like this one that was like a quarter of the size.
And the big one is just for that peak use on the hottest day of the year, essentially.
And I don't even know if it got used then because it was like 4 times too big.
So I've seen technologies where with the ventilation system, with fan coil units, ACs and stuff like that, they can ramp up the fan up and down or the cooling/heating up and down as opposed to just being on off. Is that becoming more common? Do you know? Have you when was the last time you worked in the ventilation space and seen like the bits and bobs like the?
So this is it's interesting because most of our work is building enclosure work.
Yeah.
And we don't necessarily touch the fans and the ducting part of it. But the space between your outlet grill and your building enclosure, that's actually where we do get involved quite a bit.
Sure, exactly.
So we cross over into that space and talk about mechanical plant quite a bit. There are much more sophisticated engineers now, and I think efficiency is becoming a driver of a lot of these buildings in mechanical plant. 10, 20, 30 years ago, it wasn't. It was just draw ducts on page, please, with fan. And
make big enough to be good.
Yeah, and ventilation rate equals this number. And people weren't concerned about energy use.
Yeah.
And I think now it's come the other way. It's like probably the biggest driver is energy use. And now you're seeing things like, we don't want to use the max ventilation rate. We want to ventilate based on the occupant load, which with CO2 monitors, for instance, or we're going to only ventilate with when the humidity reaches over a certain perspective. So way more sophisticated in the controls part of things. I'm assuming it's sort of what we see or what I would expect to be the typical industry standard.
And we try to kind of, I guess, help out with that by making a building enclosure that makes it such that you don't have to use your mechanical systems as often.
Yeah,
that's
a really good point. So if you have a really good building enclosure, the primary variable that's affecting the inside temperature and humidity and all those things is what's happening outside. So if you create a really good enclosure that stops all that stuff from getting inside, your plant size goes down and the complexity of the plants goes way down. So you get a very simple plant that's dealing with very small changes in actual load inside.
And you're just basically topping up a little bit, not like fully heating, fully cooling from scratch, essentially.
Yeah.
I think the one other thing that I kind of want to mention, because I've had these conversations before, the difference between, so there's air changes per hour, and sometimes that could be talking about ventilation systems, and sometimes that could be talking about infiltration through the building envelope.
Yep.
Let's just kind of flesh that out a little bit.
Yeah. Okay. So air changes per hour there's a bunch of different ways you could measure ventilation rates.
Sure.
Air changes per hour is one that is commonly used, and it refers to replacing all of the air in a room in 1 hour. So that's one air change per hour is all the air in the room gets replaced in 1 hour. As a rule of thumb, ventilation, you might see somewhere in like the 0.3 air changes per hour, 0.5. Depending on what you're doing in that space, what you're ventilating for.
Sometimes it's per occupant, or does that go to liters per hour?
There's 2 parts in ASHRAE 62. One deals with like the floor area, and then one deals with the activity you're doing that floor in that space. So if you're doing something sweaty and whatever,
gym, pool,
you'd have a higher activity portion per occupant than in the
Just a residential space or something like that.
Yeah. So that's the ventilation side, air changes per hour. You can also convert that to meters cubed per second, would be the other way to measure ventilation rate. And you just figure out the volume and do some math, figure that out. Air changes per hour through the building enclosure is air leakage.
Correct. Infiltration.
That's commonly done under a test scenario at either 50 pascals or 75 pascals.
With a blower door test, pressurize or depressurize the inside, check how much air is going through.
So you're creating an artificial pressure such that you can then measure it.
That's also measured in air changes per hour. And like for a passive house, I think it's below 0.6 air changes per hour at 50 pascals is like the number that you have to get to for air tightness. But air tightness, air changes per hour, and ventilation air changes per hour are unrelated. They are separate things.
There's a rule of thumb you can apply.
Oh, okay.
The rule of thumb is your ACH 50 or air change per hour at 50 pascals.
Air tightness, infiltration.
Yes. Your infiltration under test conditions is about 20 times higher than your actual in-service air infiltration rate you might get.
Because of the fact that with a building, if you're doing an air tightness test with a blower door, you're pressurizing or depressurizing the whole building. All the surfaces are either being pressurized or depressurized. Whereas if you have wind blowing against your building, it's blowing against one side. So you got positive pressure on this side. You got some negative pressure on those sides. Maybe you have some positive pressure or negative pressure on the lee side.
Well, effectively, you're creating artificial, under the test condition, you're creating artificial pressure such that you can measure it in a way, but you're not going to see anywhere near those pressures in service.
Correct.
Because wind's not constantly at 50 pascals.
Yeah.
50 pascals is like... I think it's 35 meters per second.
And that's constant pressure.
Constant pressure, yeah. And around, like you're right, around houses, it's very complex in how air moves. Yeah. But back in the probably 80s, 70s, 80s, brands did some work on this, trying to correlate the test conditions to that in-service and use tracer gas to sort of do this comparison. Long story short, if you didn't have anything else to go by, divide by 20 would get your natural air infiltration through the enclosure. Which you can pretty quickly figure out it's not going to be enough to ventilate your house.
Yes, if you have your windows closed. If you have them open, maybe you're going to blow through.
So if you did a blower door test and at 50 pascals and you got an air change of 2, that means your effective is going to be 0.2 air changes per hour.
Based on just wind blowing.
Did I do that right? No, 0.1. 0.1 air changes per hour. Divide by 20.
20, yeah. Cool.
0.1.
Yeah.
And we're talking about we're needing 0.3 to 0.5 air changes per hour.
Yeah. The other interesting thing, so obviously that's not really going to work, just having air blow against your building. Even if it's super air leaky, technically you're not going to have enough ventilation. The other time you're not going to have enough ventilation is by opening your windows, because if you actually wanted to get full ventilation and have constant ventilation in your house and have constant good air in your house, don't you have to open your window like 10 minutes of every hour of every day or something like that? I feel like someone did a calculation to kind of work out.
You can replace all the air in your room in, I think it's 10 minutes per hour.
Sure.
Under some sort of wind pressure and some sort
based on assumptions.
Yeah.
Temperature inside, temperature outside.
That feels right. Like if you burnt some bacon and it was smoky,
10 minutes
and you
with the windows
open the windows open for 10 minutes, you'd probably replace all the air in there.
Depending on the size of the window, depending on the direction of the wind, et cetera, yeah.
And if you happen to hit that on a day that's comfortable outside,
great.
But
if it's in the middle of the winter,
98% of the year, that's not the case.
Yeah. And like that's the other thing. A lot of people want to have operable windows. I don't argue with that. It's nice to be able to open your window, but I've had conversations in project meetings and things like that where I'm suggesting, let's put some heating in, let's put a ventilation system in, because no one wants to open their windows in the winter. Some people do. It's probably the same number of people that use their trickle vents on a regular basis. Probably that same percentage will actually legitimately open their windows enough during the day to have it be enough ventilation.
I did live when I the first week I moved to Auckland, New Zealand.
Yeah.
We were in a Airbnb situation. It was like a room.
Sure.
It was a family owned the house and they had like 7 or 8 rooms in this house.
Okay.
And we were staying in one of them. And the mother in this house was absolute stickler for first thing in the morning.
Open the windows.
Every window in the house open for an hour
When I first got here as well, I went to go visit a friend in Gisborne, and she was living with a few different housemates. And one of the housemates, every single morning, every door, every window, every blind, everything's open for like an hour and then closed back up.
It's like so cold.
Yeah.
Breakfast is so cold. But every morning.
But like technically, with an older building, that makes sense. And if you run your building like that, then yeah, you can exhaust a lot.
It's old building, but yeah.
Okay, fair, sure. But I mean, technically it works. But it works at that time. What you're doing is you're clearing out the moisture from everyone sleeping, maybe some showers in the morning or at night, clearing out that moisture, and then
if you've got nothing else to do, if it's the only means of ventilation, then that's what you got to do.
Cool, fill your boots. Why not? Yeah. But if you have a ventilation system, it might make your life a lot easier. Because mine is a lot easier. I don't have to go open all my windows every morning. I used to.
Well, the thing I think people like to open their windows if they have a bad ventilation system that doesn't work.
Correct.
Like operable windows make up for a bad mechanical system.
Correct.
If you have a good mechanical system, you probably don't need really openable windows.
Yes. It's just a nice to have as opposed to a necessity. Yeah, exactly. Any other things about ventilation? I think we've covered most of it.
We could go on and on for days about ventilation.
Sure.
The ASHRAE 62 standard, 61.1 for commercial space, 62.2 for residential, is a really well researched, really well developed standard. It keeps changing like little bits here and there.
But that's
keeps evolving, but it's like 80 years old.
Yeah.
Like it was like based on like rules of thumb, and like I said at the beginning, used to be based on smoking rates.
Sure.
Like how much air do we need to have in this space so we don't have the smoke lingering around? Yeah. And you had a good comment about old basketball footage.
Yeah. I saw a TikTok where it was like some guy comparing a photo of like 2025 All-Star game or something like that versus the 1985 All-Star game, making up dates here. So don't quote me on that, but basically showing the difference of photography, and one clearly looks a lot better, and it's the 1985 one. And the reason for that is because there's a haze in the background. So you have these guys like jumping up, doing a dunk or something like that. Theatrical, yeah. You got this
theatrical smoke.
Yeah, haze in the background. Everyone kind of blends into the background. You don't really see the audience too much, but just like a little bit. And it looks so much cooler. And it's because everyone was smoking inside the stadium. And they had, enough ventilation, but not enough to keep it clean. It's very interesting to think about, because now in theaters, usually you'll have like a mister, as opposed to like a smoke machine that puts in a big puff. It's like a very small amount to just have haze. And I feel like maybe they didn't need that back in the day because everyone was just smoking in the theater. And that was like a new thing that had to be developed.
Yeah. So now you have to artificially create smoke.
Correct.
That's healthy for you.
Correct. Yeah. They could just give everyone a pack of cigarettes and a lighter as they walk in, everyone light up in Act 3, Scene 2. Make sure you all light up. Could be interesting. I think that's about it for ventilation.
I think we covered a lot there.
Yeah. Build tight, ventilate right. It's on my wall. I got a little sign there. It's always in the background.
I'm actually going to change that.
Oh.
My saying is ventilate, period.
Okay.
Then build tight.
Okay. You know what? I don't mind that.
In terms, just do any ventilation.
Sure.
Even if you do it wrong, you're still going to be better off than...
There's more air. There's more molecules of air that can pick up moisture. They can give you more oxygen.
Actually like... If you just ventilate the space using any
positive,
any
negative,
equipment you
balanced
want,
fan, inline fan,
sort of hard to fuck up.
Big leaf, yeah, honestly,
sort of hard to fuck up.
Just put more air.
Your range of fuck up is between like efficiencies and those sort of things, not between like
life and death or anything like that.
Yeah, I mean, ventilation is probably not life and death. A lot of cases. Well, I mean, asthma is life and death for people.
It can be, and depending on how airtight the space is, maybe it is. But anyways, I think that's about it for ventilation, and we'll see you again next time. Yeah.